Hello, PowerMax here, and today on Weekend Projects we're going to be building a plasma speaker. It's also called a singing arc, and it's a type of flyback driver. Now, other than just creating pretty sparks, you can also make it musical. Okay, I'll stop.
Alright, now let's build this circuit. Now the main part for this flyback driver is of course going to be a flyback. Now, although you can rip these out of old TVs, at least in the States, as far as I know, it's technically illegal to be dumpster diving, so I didn't go that route. I just bought one online for like $16 from eBay. It was literally like the cheapest thing I could find, and it actually works out really well. You're also going to need some active components, namely the 555 timer. You can buy these at like jamnico.com or some other online resellers like DigiKey or Mouser. And you're going to want to buy those in quantity because you're going to be burning these out quite a bit. And you're also going to want to have a lot of transistors. Now in this case, the only transistor that we're going to care about is the RFP 250N. Now I've actually printed out the data sheet for this particular transistor. And these are the types of ratings that you want to look for if you have another transistor that you're curious about. So if you don't happen to have the RFP 250 but you've scavenged other transistors out of like old power supplies, out of old switch mode power supplies, that's a good place to find these types of MOSFETs. They might be in a different package type. They might be in the TO220 kind rather than this package right here, which is the TO247. Anyway, here are the ratings that you're going to look for. You want to make sure that the on-state resistance is as low as possible. Now this isn't the lowest on-state resistance, but it's pretty good. And the rating is at 10 volts, so it's close enough to 12, which is what we're going to be using. You'll also notice that the voltage from drain to source is 200 volts. Now you want to make sure that's at least 200 volts. If it's any lower, then it's very likely you'll burn out your transistor from too much voltage. And the reason for that is you might be saying that, well, we're only powering with 12 volts, so how are you going to get 200 volts on the primary side of a transformer? And if you're curious about that, Google EMF kickback or high voltage kickback or the flyback effect. It has to do with inductors. When you have a lot of current flowing through an inductor and you were to stop the current flowing through the inductor as quickly as possible, you'll see that you're going to get a really big voltage spike when you stop the current flowing. So the EMF kickback from the flyback is capable of destroying the transistor and of course the 555 and everything else on the primary side of the circuit. So you want to watch out for that. And the other rating you want to look out for, and this is going to be related to the on-state resistance, is the continuous drain current. You'll notice that this one supports 30 amps when you keep the MOSFET nice and cool. However, it's really hard to keep a MOSFET that cool when it's under high load. More likely, you're going to be operating closer to the 100 degrees C. And you can look into the thermal equations for the thing. This is why we need such a large heatsink. So that's another thing you'll need. You'll need a large heatsink and maybe some active cooling too. Now, it turns out after I built mine up, I was drawing close to 8 amps short circuit on the output of it anyway. And when I had on a different configuration with more power, I was getting upwards to 12 amps. So, I was really maxing out my Xbox power supply. Anyway, yeah, so make sure your transistor is good. You're also going to need a couple of miscellaneous components. Now here I've got a large electrolytic capacitor. That's to smooth out the 12 volt rail that we're going to be powering it with. And we also have a smaller film capacitor, and that's to make a tank circuit with our flyback, because we're going to be actually working it with not in its flyback mode of operation, but rather in its resonance mode of operation. So the circuit's a little bit different. You get hotter sparks, same voltage, but the advantage of having that capacitor there is that it absorbs a lot of the EMF kickback from the capacitor, and it actually uses it to create a resonant circuit between the two, so the circuit will operate more efficiently and you'll get hotter, brighter arcs. That also means the circuit's going to be a little bit more lethal, so you want to make sure you don't touch the output. You're also going to need either a perforation board or a breadboard. Of course, the 555, you're going to need some miscellaneous circuitry for it. I've got 2 Zener diodes, and the reason for the Zener diodes is to clamp the gate's voltage so that it does not exceed wherever the rating is. If it's even on the first page, here it is right there. The gate to source voltage. The gate, which is the input to source. You want to make sure that does not exceed plus minus 20 volts. Now these Zener diodes are rated for 12 volts. So they're gonna prevent the voltage on the gate right here from exceeding plus or minus 12 volts. That's important. If we can eliminate one of the things that might cause this circuit to go wrong, why not? You know, so because this is a very high impedance input, it's very easy to raise the voltage way beyond its limits, even with just a static discharge. In other words, these things are static sensitive, and this thing produces static electricity in a way because it's a high voltage DC output. Anyway, you're also going to need some 10K resistors, a 1000 picofarad capacitor, of course the 555, and a little electrolytic capacitor. Alright, so here's the schematic. The way it works is simple. All it is an astable 555 timer connected to the gate of a MOSFET, which is just simply an electronic switch. As the output of the 555 pulses on and off, it turns on and off the transistor, and thus it varies the current through the primary coil. Because the flyback transformer is in fact a step-up transformer, any small change in voltage on the primary side will translate to a really large change in voltage on the secondary. You may notice that I'm using dual supplies, but this isn't necessary. You can actually power everything off of the 12-volt rails. However, this means that the circuit will be a little bit less reliable. The reason for this is if you're drawing a lot of power from the flyback and you cause a brownout on your large power supply, that brownout is going to translate also to the 555 circuit, and it may cause it to latch up and cease working, and this will cause your transistor to die pretty quickly. And also, if you're looking to get more power out of the circuit, then your only option is to use a higher voltage power supply, and also one that can deliver more amperage. By raising the voltage, you'll end up pushing more amperage through the primary winding on the flyback, and that of course translates to bigger, hotter arcs. Alright, I've droned on for long enough, let's actually build the circuit. Alright, to start building the circuit, let's build a low voltage section first. You're going to take your 555 timer and insert it into the breadboard right there. Doesn't matter where it is. Just make sure that the notch in the top corner, or the little black dot, is facing upwards. If you mount the 555 upside down, then you will allow all the electrons to fall out, and that's a bad thing. You don't want the electrons to fall out. The next thing you're going to do is you're going to take your power wires, the things that will take power to your 555, and you're going to connect pin 1 to the ground. I hope it can reach. You should probably use the other ground pin, but I like this one for some reason. Maybe because it's the burn mark, I don't know. Then you're going to take the other power wire, and that's going to go between the pin 8 and your positive rail. Okay, then now you're going to take your capacitor, your little 1000 picofarad capacitor, and you're going to put it between pin 1 and pin 2. The polarity of course doesn't really matter with the ceramic capacitors. Then you're going to take the 10K resistor between pin 8 and pin 7, and another one between pin 7 and pin 6, and then one more wire between pin 6 and the pin 2 where the capacitor is, right there. And then lastly, we're going to take these diodes, and we're going to actually connect them backwards to the standard way. So we're going to have the negative end of this side go off to the positive of our power rails. Eventually this is going to be the input to our MOSFET, and of course we want to clamp it so it cannot go above the power supply rail. And this diode is going to clamp it to prevent the voltage on the gate of the MOSFET from going below the negative rail. And that's going to go between the negative and pin 3. Now you'll see, I'm not sure if you can make it out in video, but the black ribbon around the diode is facing right here. It's facing here, and this is of course connected to the negative. So the diode looks backwards. And that's to reverse bias. It should not normally conduct electricity, so we're purposely doing that, connecting it backwards. But when the voltage here gets too high or too low, it will force this diode to conduct electricity. It's just the way diodes work. So anyway, now that we've got the low voltage section all wired up, after of course we take our capacitor and wire it between pin 5 and some random point of the circuit. This is going to be tricky because I don't want to interfere with those diodes. Doesn't really matter where the spare pin goes, that's just going to be our audio input, so that's where our audio will connect in. And it doesn't really matter the polarity of it because it's just AC, it's low voltage AC anyway. So anyway, you want to verify that this thing's actually oscillating, and that can be a bit tricky, but one of the ways you can do it is raising the capacitance here just by adding another capacitor, and then just tacking on a little speaker to the output, a little 8 ohm speaker, and seeing if it makes a nasty whining, hissing noise. But the better way to do it is actually to use an oscilloscope. Now I so happen to have an oscilloscope, so that's the method I'll use. I'm just going to tack on a little wire here to pin 3, which is going to go to the MOSFET. And I'll take my probe, and I'll connect it up to that, right here to pin 3, and the other end is going to go to ground. So anyway, now we know that the circuit is in fact oscillating. That's a good thing. Now we can connect up the high voltage section of the circuit, or the high power section of the circuit. So we'll remove our oscilloscope probes. So then we're going to take our transistor here, and we're going to refer to the data sheet to figure out the pinout. And in this case, it's the TO247 AC package type. And you'll see that this is the pinout. Ground, source, and drain. And that corresponds to ground, source, and drain here. So we need to wire those respectively. So first you're going to take your drain pin, or I'm sorry, your gate, and that's going to go to the input of your 555, or your output of the 555, I mean. And that's going to drive the gate. And then these other two outputs right here are going to go off to our higher voltage, and also our 12 volt rail, and also our flyback transformer. I'll bring that into shot right now. Alright, now we are going to take our flyback transformer here, and we're going to wind some wire around here. I've already done this in the past for a previous ZVS driver circuit. I'm just going to be using the same wire, and I found that 4 turns of wire around the core actually works really well. Now the polarity of the way that you connect this up will matter. If you connect it the wrong way around, it will still work, but the output will be diminished, and you're going to be fighting against the internal capacitors in here, inside the flyback. Especially if you're doing this in a flyback mode, and you're not doing this in the ZVS mode. But anyway, you're going to connect one of these pins to the center pin on your transistor, the drain. Now I'm going to take my capacitor here. This is very important. This is going to really make sure the output is reasonably good. And you're going to want make sure that the polarity is correct. This is the negative end of the supply. Oh, I'm sorry. The negative end actually goes to the source of the transistor right here. And this is going to be the positive. Okay? So hopefully that makes sense. And I'm not connecting these to the circuit board for obvious reasons. I would have preferred to do that, but clearly the board down there doesn't really like the high voltage. Anyway, then we're going to take our last capacitor right here, and we're going to wind it between the connection between our transistor or our MOSFET and the flyback windings right here. Solid wires, hard to wind. And then the other side of this is going to go to one of the power supply rails. It doesn't matter which one because of the capacitor action, the way capacitors work. Now the last step is actually to make a connection between one of these pins, one of these power pins, actually the ground pin to be specific, and our ground. So we're going to take this capacitor output. I'm going to take it up just a little bit. This is the negative side. That's going to go to the negative. You'll see that I'm actually powering this with dual supplies. I'm using a lower current 12 volt regulated power supply to power the 555. And I'm going to use my high current 12 amp power supply to power the flyback. That's not necessary. You can power it all off the same supply. And in fact, that's what I was doing earlier for quite a while. Works perfectly fine. But I just happen to like the convenience of doing it this way. So anyway, there are also advantages associated with a separate supply, meaning that whatever goes on the high voltage, high power side, it's not going to be carried over to this over here. So filtering of the power supply rails is not as critical. Anyway, then we're going to connect this up to the 12 volt. This is our high power 12 volt supply. And this is important that everything has a common ground, and that's very critical. My two power supplies are completely separate units, and so they're isolated from each other. So it's important to have them not isolated from each other. And then we are going to carefully touch these together, and we're going to listen if this thing makes a lot of hissing noises. Hear that? It works. That's good. The only problem is the output is not all that great. Alright, after some tweaking and some further figuring out mistakes I've made. I had to do some troubleshooting off camera. I couldn't really conclude what was the problem. It's just that this circuit is really finicky, and when you're using breadboards, wires come out very easily, and it's just a mess when you have all these twisted wires going every which way. Anyway, I do have the circuit built correctly, and I've tested it. I did have to swap the wires, I believe. I actually swapped them back and forth a few times to see if it made a difference, and it does make a difference. You'll get twice as much length out of your sparks if you have it connected the right way around. Anyway, so here I've got the negative, and from right here going over to just a pair of helping hands. Helping hands are pretty cool, they're nice and helpful. Anyway, and here's my high voltage scary wire. And when you're touching the high voltage scary wire, you want to make sure you're either on the insulation, or better yet, you have a chicken stick, where you actually take a board, insulated material, and you have kind of a long stick that you hold onto the thing for. This isn't high enough voltage for me to really worry about that. Alright, now it's time to actually use this circuit. Now you'll notice I've actually wired up a fan right here to provide some active cooling, because I was running this circuit just a second ago off camera, and this transistor was getting smoky hot. It was probably still within its rating of 100 degrees C. However, this heatsink was pretty hot to the touch, and I decided to add the fan as it's necessary. It's only blowing at a really low speed through a couple of resistors here across the 12-volt rail, and that's actually another reason why you should use a second isolated power supply. Is that way this thing produces a lot of electrical noise on these lines right here, and that feeds back. If this feeds back into the primary for this side, that noise, you'll actually hear it on the arc itself. And when you're trying to use this as a singing arc, any amount of additional noise in that arc is not good. You want to hear the music, not the noise the fan is making. So that's another thing to watch out for, especially if you're using a power supply that just barely is able to deliver the current, like one of those big transformers with the not regulated output. You have a lot of ripple there, and you're causing the core to saturate, and the voltage is dropping and sagging all over the place, and it's just a mess. So yeah. Anyway, we're going to wire this thing back up again, and we're going to test the output. So when you first go to power up the circuit, listen if it's making a hissing, whining sound. You'll hear it's actually crackling, and that's actually arcing internally right there on that pin. It's actually arcing to the ferrite core. Let me see if I can't fix that after discharging the coil there. And you will want to put some sort of a silastic all over that, some sort of hot snot, hot glue, whatever you want to call it. In fact, the better thing to be using would be called Corona dope. That's actually some purpose design stuff specifically for that purpose. But anyway, we'll connect this back up to power again, and we'll see what the output looks like. It's not a bad output, but eventually, at least for my circuit, which is a bit weird, but it'll eventually start acting like a ZVS driver instead. I'm not exactly sure what causes this, and I'm not gonna complain about it. And you can see we're getting, we can start arcs at around 2 centimeters, and they can grow as long as 3 to 4 centimeters long. Yeah, look at that. That's almost like that's pushing 4 centimeters, 5 maybe. I got plenty of Corona here to deal with. Alright, now let me turn off the circuit for just a second. Short out the output, and make sure my transistor is running cold. Yep, heatsink's just warm, just a little bit warm. Without active cooling, this heatsink would be already pretty hot to the touch. So the active cooling is important for the circuit, especially for continuous operation. You want you want the fan there at least to turn on when the heatsink gets too warm, if you plan to make this into a permanent project. Now let's connect up the audio. For the audio, we're going to need a audio plug of some sort. This is just one I've kind of put together real quick from a audio plug from Radio Shack when they still used to be around. They probably are around in your local area. You'll have to look around. My Radio Shack is still open, though they don't have much of a selection of parts like they used to. Anyway, then we're going to connect one end to the ground rail, and we're going to connect the other end to that capacitor we connected, this yellow capacitor right here. Make sure those power supplies aren't shorting out. The other end goes right there. Alright, now all you need to do is turn on your radio, max out the volume on there, make sure it's tuned to a station. Let's connect this thing up. Now you can hear it's musical! Now I don't want to have this play for too long at a time because I don't want to get caught up into the YouTube monetization and copyright infringement and all that bull crap that goes on. So I'm not going to let you listen to the whole song. And I'll probably mix this up in editing so it's not continuous anyway, just to be double sure. One of the things is the bass response is actually pretty good. Alright, you might notice that I've changed out a few things, and there are some very good reasons for that. I was experimenting with different number of windings, different voltages. I powered this thing up from 24 volts, and I was getting some pretty sick arcs. I was starting my arcs at around 2 inches, and I was able to stretch them out to like almost 5 inches, with tons and tons of corona. However, my Flyback Transformer didn't necessarily like that, and I actually ended up killing my old transformer. What had happened was that it started to arc over to the primary, and of course you know that whatever it arcs over to, it starts to carbonize. So I took an X-Acto knife and I just started scraping away all the carbonization. But once the carbonization started, you really can't do anything about it. So I just put a whole bunch of hot glue there, I soldered a wire to there. And I think I might have also killed the internal rectifiers inside of this thing, because it started acting a little bit more like an AC flyback, and I was seeing a lot of corona build up around the core and the coil itself. And so that kind of scared me from trying to use this anymore. I can still get arcs out of it, it still works. However, it's just making a lot of hissing noises and it's very lossy now. The core gets very warm. I'm not really sure what's happening. It might be actually shorted internally. I don't know. These flybacks are a bit complicated and they're easy to overload. They're really not designed to be pushed as hard as we're pushing them here. So anyway, I've got another flyback from a previous project that I've built, set up here temporarily. And while I have it here, I've also changed the primary some. And of course I've played around with the circuit some more too. And I'm not going to be powering this thing off of 24 volts again. I don't want to risk burning this transformer out. So anyway, I'm now going to show you what the Jacob's ladder does. Anyway, the operation of this thing is pretty simple. What happens is you have an arc that starts down here, and as it heats up, the heat rises, and so does the plasma, and the arc actually rises along with it. But as you can see, these two wires actually get further and further apart as you go up to the top. Eventually it's too wide, and it becomes easier to start to break the arc up here and to start back down here, and the whole process begins again. It's a pretty neat little gizmo. I'll set it right here off to the side, and I'll show you that running right now. So you can see what I was talking about here. The arc starts at the bottom, and it rises up because of the hot plasma, but eventually it can't maintain the length of the spark anymore, and it becomes easier for it to cut that spark off and restart back down here at the bottom. And then it rises again because of the hot plasma. Now I'm sure you'll be wondering, can you play music through this while it's doing that? And the answer is, yeah, you can. So now, not only do I have an awesome Jacob's ladder, I've got a musical Jacob's ladder. You might notice that the audio quality is a little bit worse than before. Unfortunately, for some reason, this new transformer doesn't really render the audio as well as the previous one. I don't know why. But it could also be with the setup with my 555 timer and this long cable running from an amplifier. I've been having some trouble with that too. You'll also notice as it gets closer to the top, the music gets louder. And that's because there's more surface area between the spark, the arc, and the air. It's the same reason why lightning is a whole heck of a lot louder than this. You can see my voltage is sitting at right around 11.8 volts. That thing is so satisfying. You've got to admit. Alright, after changing out my Flyback Transformer, now I'm going to show you what the new arcs look like. Now you may notice that these arcs are a lot longer, and I believe this has to do with the fact that I changed out the Flyback Transformer for an older one that I've had. This older one was a little bit more expensive when I first bought it, but it's also a little bit larger. Notice the voltage on the battery, about 11.9 volts, almost 12. Look at the sparkling.